Hello all. Today we'll begin with lecture 4 of the response spectrum analysis video lecture series. This will be our last lecture on this series. In our previous lecture, we looked at model analysis which formed the basis of a response spectrum analysis. And in today's lecture, we will see how to define the response spectrum function, how to define a response spectrum load cases, and finally we will see and we will learn about the scaling of base shear. So before beginning with the definition of a response spectrum function and load cases, in which conditions should we perform this response spectrum analysis? Let's first look at that. Let me just erase this. Okay. We will see ETABS demonstration today. And our response spectrum analysis, we are also looking at this analysis procedure based on the Indian code IS 1893-2016. And what IS code says in its clause, one of its clauses, that is clause 6.4.3, is that equivalent static method may be used for analysis of regular structures with approximate natural period less than 0.4 seconds. So we can use equivalent static method or equivalent lateral force procedure in cases where the time period of our building is less than 0.4 seconds. So let us find the time period in the case of our building for which we are going to perform RSA or response spectrum analysis. Ours is a 4-story building. Since we have a staircase cover at the top also, let's say that our building is a 4-story building and the floor height of each story is 3.2 meter. So we know the formula for the time period of our reinforced concrete moment resisting frame structure. IS code 1893 in its clause 7.6.2 gives us the formula for time period, which is given as 0.075 multiplied by the height of the building to the power 0.75. So what will be the height of our building? The height of our building will be 4 into 3.2 because we have 4-story and each floor height is 3.2 meter. We get this height to be 12.8 meter. Use this value of height in this formula here to get the time period of our building. You get the time period to be approximately 0.508 second. And this time period is greater than 0.4 seconds. So we have to use linear dynamic analysis method. Since our clause, remember this clause also, 6.4.3 of IS 1893-2016 states that equivalent static method can be used for those buildings or those structures with approximate natural period less than 0.4 second. When we calculated the time period of our building, we got it to be more than 0.4 second. So in this case, we have to perform the linear dynamic analysis method. And there is also another clause in IS 1893 or in the same code which talks about the linear dynamic analysis method. If you see in clause 7.7.1, what this clause states is linear dynamic analysis shall be performed to obtain the design lateral force for all buildings other than regular buildings lower than 15 meter in seismic zone 2. So there are two conditions for which linear dynamic analysis should not be performed. One is the building should lie in seismic zone 2 and the height of the building should be less than 15 meter. So our height of the building is 12.8 meter, which is less than 15 meter. So this condition is satisfied. But Our building, we have considered that our building lies in seismic zone 5, which is the building with the highest seismic hazard. So this our building lying in seismic zone 5, this means this condition is not satisfied here. So because of this also we have to perform linear dynamic analysis in our building. So there are two main clauses in IS 1893 part 1 2016. 2016 is the revised version, which states the conditions for using linear dynamic analysis in the design of our buildings. Clause 6.4.3 and clause 7.7.1. You can download the code from the internet and look at these codes also. So once we have determined that linear dynamic analysis is required, now let us go through the steps, or let us go through the ETABS demonstration, which shows us how to perform the response spectrum analysis method. Remember that in our previous lecture, we have already done two major things. One is we have defined the mass source. I'm using the same model or same ETABS model that I used in the previous lecture. So this is locked here. Let me unlock the model and go to define and mass source. We defined a mass source with the same name, mass source. Click on this modify for mass source and you see that our mass source is based on the dead load and live load acting on our structure, and these dead load and live load contribute to the mass source. That means these loads contribute to the composition of base shear for our building. So we have defined the mass source. Let us click cancel here, and we have already defined the model case also. Go to define and see model cases. We have defined a model case of subtype eigen, model eigen. If you click on modifier showcase, you can see everything that we defined in our previous lecture. We have already talked about in detail here. We talked about the model subcase type or model case subtype. We talked about the P delta settings. We talked about maximum and minimum number of modes, and we also discussed on shift frequency and cutoff frequency in our previous lecture. So I'm not going to go through that again. Let me just cancel this. I just wanted to show you that we have already defined the model case here. So let me just cancel this. Now let's define a response spectrum function. For that, go to define functions and a response spectrum. You saw that we have two options here, define functions. We can either define a response spectrum function or time history function. Time history function is defined for a whole different type of analysis procedures. We are only concerned with the response spectrum function here. So click on response spectrum function. We have a default response spectrum defined here. So let us just ignore this. We want to define a new function based on Indian code. So from this option, choose function type to add. Click on this drop down list and choose the Indian code, IS 1893-2016. Remember that for a newer version of ETABS, there are two options available here. Either you can use IS 1893-2002, that is the older version of IS 1893 code, or you can use the latest 2016 version. So I will choose here IS 1893-2016 version and then click on add new function. So first we have to give a name to our function. Let us just give this name is response spectrum function RSF 1893. So you can give any name to this function. And function damping ratio, we will use a 5% damping as stated in the IS code. So damping ratio will be 0.05. And parameters, let us see here, these parameters should be the same that you have used while defining the earthquake load patterns, EQX and EQY. So remember to put the same parameters here. Our seismic zone will be 5. Our seismic zone factor for our 5th zone is 0.36. Our importance factor is 1. Our soil type is 2, that we have considered medium soil type here. And our response reduction factor will be 5 for ductile moment resisting frames or special moment resisting frames ASMRF. So for these parameters and for this damping ratio of 5%, we get the response spectrum curve here. So I zoomed a little here, we get this response spectrum curve. And you can just hover onto this curve here and get the different combination of values. If you remember, the horizontal axis of this response spectrum curve is time period, and then the vertical axis is the spectral acceleration. So each point on this graph represents a combination of these two values. So this is our response spectrum curve, and our response spectrum curve is plotted in linear fashion in both x and y axis. So leave this plot option as linear x, linear y, and then click on OK. So we have defined a new response spectrum curve here, RASF 1893, and then click on OK. Now after you have completed the defining response spectrum curve, you have to define load case for the response spectrum curve or for the response spectrum function. We know that load case tells us how a particular load is applied to the structure. Simply defining any load pattern or simply defining any response spectrum or simply defining any function will not apply that loading to our building. Our each function or our each load pattern should be associated with a load case in order for that load to be applied. So now we have to define the load case for response spectrum. So go to define and load cases. You can see here that load cases has been already defined for our all other static load patterns: dead, live, masonry, partition, floor finish, EQX and EQY. We want to add a new response spectrum load case. For that, go to add new case and then insert the parameters in this load case data. Our load case name, you can put any, but put that name which will be easy to identify later. So I will type this as just response spectrum, RESP. And our load case type will be, if you click on this drop down menu, our load case type will be response spectrum. Since it is a response spectrum analysis, our mass source used is the previous mass source, which is this mass source. Since we have only one mass source defined in this model, that will be our default mass source, and the same mass source will be used in this load case also. Analysis model default, it is the default parameter here. Now we have to select loads applied for our response spectrum load case. So what will be the loads applied? If our let me just erase this at first. We know, let me draw here our response spectrum curve first. Is defined in our IS 1893 code. We have natural time period T in seconds in the x-axis, and we have SA by G in the y-axis. SA is our spectral acceleration and G is our acceleration due to gravity. So you can see that SA by G is unitless. Since both numerator and denominator are values of acceleration, when they are divided by each other, then this factor is unitless. We can say that the value of this spectral acceleration is normalized, and it is normalized by the acceleration due to gravity. So our curves were somewhat like this. Starting from 1 year, our response spectrum curve were something like this. This was our response spectrum curve, and we had 1 second, 2 second, 3 second, 4 seconds and something like this. So this was our response spectrum curve for, or this was our spectral curve for response spectrum analysis. And if you see here that we have values of SA by G, that is normalized value of spectral acceleration in the y-axis and the value of time period in the x-axis. So when modal analysis is performed for our building, then we get different modes of vibration, and the number of modes of vibration is dependent on the number of degrees of freedom in our building. And we also know that each mode of vibration is associated with a particular natural frequency or with a particular time period. We saw in our previous lecture that the lower modes have the higher time period, and generally for shorter buildings or buildings of lesser height, only the lower few modes contribute to the total response of the building, and the higher modes are generally negligible. So here, as we know that our mode shape or the mode of our building is associated with a particular or definite time period, we can plot values of different time periods on x-axis in this fashion, corresponding to the different modes of vibration. And we know that, first let's see here, we have three curves here. These three curves represents the three different types of site classes. The lowest curve represents the site class type 1, which is rocky or hard swell. The second curve represents type 2 or medium swell, and this third curve at the topmost represents type 3 or soft swell. So now we can draw a vertical line from these natural time periods, which correspond to different modes of vibration, to the corresponding curve. We have considered that ours is a type 2 or medium swell. So from these points, just draw vertical lines from these points of natural time period to the curve. And then from these points, draw a horizontal line here. Remember, this is just a conceptual framework, and this may not represent the actual time period. I'm just giving this as an example. So corresponding to these different modes of vibration, we got different time periods, and for these corresponding time periods, we got different values of spectral acceleration. And these acceleration are now the loads that are applied to our structure. So you get this? If you don't understand this, let me repeat once again. Response spectrum analysis is a multimodal or multiple modal combination method in which, as we have already discussed in our previous lectures, the responses from different modes of vibration are combined, and that combination is done using a particular combination rule. We touched upon the combination rule in our previous lectures, such as SRSS method, CQC method, or absolute sum method. So what a response spectrum analysis does is it combines the responses of our building from different modes of vibration. And to get the response from each mode of vibration, what is done is that the acceleration is applied to our building corresponding to each mode of vibration. For example, for the mode represented by this time period, we get the acceleration value to be this much. For the mode of vibration corresponding to this time period, we get the acceleration value. Although it is normalized, we can still say that it is the value of acceleration. We get this acceleration value. So these acceleration are the loads that are applied in the case of response spectrum analysis. So going back to our ETABS model, our load applied will be acceleration. So let us add two accelerations here in the two horizontal plane directions. We will not include any vertical acceleration here. That will be an advanced analysis. We will just include the two accelerations in the two horizontal plane directions. So first acceleration will be in u1 direction and the second acceleration will be in u2 direction. And the function associated with this acceleration will be the response spectrum function that we defined earlier. So click on this drop down menu and select RSF 1893. Also for the second acceleration, click on this RSF 1893. And finally, there is an important concept here of scale factor. So what value should we use as scale factor and what does this scale factor means? Let us look at now. Let me erase this. So what we saw in our previous graph was that if this is our spectral curve for response spectrum analysis, the vertical axis gives us the value of ESA by G and the horizontal axis gives us the value of time period in seconds. So we can say that the spectrum ordinates defined within our code and also various other codes that we may look at are normalized values. These spectral ordinates or these y-axis values are our normalized values in which our spectral acceleration are divided by gravity acceleration. You can see here the spectral acceleration is divided by gravity acceleration and we get the normalized values of y coordinate from this graph. What we should do when performing response spectrum analysis is that this spectrum must be converted to the specific set of units which we are using in our model. Is this value of ESA by G, this is the acceleration that will be applied as load to our buildings, but this acceleration value is unitless here. ESA by G is unitless here. Now what we have to do is we have to convert this unitless value to the units of acceleration that we are using in our model. Units of acceleration that we are using in our model. So our scale factor should be such that we convert this unitless value or unitless and normalized value of acceleration to the units of acceleration in our model. And how do we convert that? We convert this by multiplying with G. Simple as that. This SA has been normalized by dividing by gravity acceleration, and we can convert this to the unit value in our model by just multiplying by G. So this is the way that we can convert the spectral ordinates by multiplying by the value of gravity acceleration. But this gravity acceleration, the units of this gravity acceleration should be the unit of acceleration that is used in our model. Let us go back to our model and see what units are we using. So I will just cancel this here. I will come back to this again. I will just cancel here. I will go to units and go to show units form. Scroll below and see that in this time related parameter, our acceleration, whether it is translational or rotation, is defined in the units of millimeter per second square and radian per second square. So see here and note this carefully that our translational acceleration is defined in the units of millimeter. Second will be the same for all. It is defined in the units of millimeter. So this G also should be used in the units of millimeter. That is, G will be now 9810 millimeter per second square. So we have to multiply this, we have to use this scale factor to convert our unitless spectral ordinates to the units of acceleration used in our model. But there is one more catch to it. We just can't multiply this SA by G only. We also have to remember that this design spectrum that our IS 1893 code gives us is a spectrum based on the maximum considered earthquake, MCE level spectrum. And this now what we should do is that maximum, we do not have to design our structure based on this maximum considered earthquake. This maximum considered earthquake MCE level spectrum should be reduced by a value of 2R, where R represents the response spectrum factor. We have to what reducing this spectrum by 2R gives us is that we divide every spectral value or every y coordinate value that we obtain from this MCE level spectrum by 2R, and thus we then reduce the value of these spectral ordinates. And finally, we also have to include a factor which is the importance factor in our scale factor. And considering these three things now, the importance factor, the value of 2R, and this value of G, our initial scale factor or SF that we should state while performing the response spectrum analysis will be importance factor I into the value of acceleration due to gravity in the units that is used in our model divided by 2R. This will be our scale factor in the initial run. And when we perform the analysis once and do base shear scaling, then the scale factor will change at that time. But for the initial run, this will be our scale factor. So what is our scale factor? The importance factor of our building is 1 into 9810 millimeter per second square divided by 2 into 5. So our initial scale factor will be 981 millimeter per second square. So let me check this again. Our initial scale factor will be Ig divided by 2R. I is the importance factor, G is the acceleration due to gravity, which is 9.81 meter per second square into 1000. We get this to be 9810 divided by 2 into response reduction factor for our building is 5. This will be 2 into 5, 10. If we divide by 10, we get 981 millimeter per second square. So this will be our scale factor here. I hope you understood the concept of scale factor. So let me go to define and load cases again. I will add new case here. It will be RESP SPEC. Load case type will be response spectrum, and our loads will be acceleration in U1 and U2 direction based on response spectrum function that we defined earlier, and our scale factor will be 981 for both directions. Now once we have defined this load applied, now let us come to this other parameters. Our modal load case will be the modal load case that we defined in our previous lecture, that is lecture 3 of the response spectrum analysis. Our modal combination method is, there are various combination methods for modal combination rules: CQC, the complete quadratic combination; SRSS, the square root of sum of squares; the absolute combination method, and other. CQC is the best method, so I will use here CQC. Include a rigid response, we won't be needing this at the moment. And directional combination type, I will leave this directional combination type as SRSS. So you may, if you are paying attention and if you have noticed carefully, what we have done here is that we have applied acceleration in two directions in a single load case. You may think how this is possible. How can earthquake be acting in two directions, or how can earthquake forces be generated in two directions simultaneously? You may think that either the earthquake forces should be coming into this x direction or y direction, but how can earthquake forces generate, or how can these acceleration forces be applied in the structure in two different directions in a single load case? That this problem is solved by this concept of directional combination type. So what actually happens is that there are several sources of uncertainty when determining the direction of the ground motion for the seismic analysis of structures. You cannot say that a particular earthquake force will be generated in a particular direction. Our earthquake forces generally do not or may not develop in the principal plan directions. That means in the x-axis or in the y-axis of our building, our earthquake forces may not generate parallel to those principal plan directions. There will be uncertainty in the ground motions. So what designers often don't know is that in which direction the largest ground motion will occur at a site. They can determine exactly in which direction the largest ground motion will occur. There will be uncertainty about which direction of ground motion creates the maximum demand on structural members. Hence, what we do is that we combine the earthquake forces in different directions using the directional combination type. So, for this case, we have used the directional combination type as SRSS. The modal damping, for now, we will assume that our modal damping is constant damping for all modes, which is 0.05, and diaphragm eccentricity we will not consider at the moment. So our load case data for a response spectrum function is completed. I will click on OK. You see here our load case of response spectrum has been added. So then click on OK. Now we have completed all the definitions that we have to perform upfront while performing response spectrum analysis. Let us just go in brief what we did. First, we checked if a response spectrum analysis is needed or not based on different codal provisions. Then we defined the modal load cases, which we saw in our previous chapter or in our previous lecture video. We defined mass source. And in today's lecture, we first defined a response spectrum function, and then we defined a response spectrum load case. Now we are ready to perform analysis of our structure. So go to Analyze and set load cases to run. At present, we want to run all load cases. So click on Run or Do Not Run All. Click on Again. Now all load cases has been set to run here, including response spectrum. And now click on Run Now. If you select all the load cases to run, it may take comparatively more time for the analysis model to be complete. If you select fewer load cases, the analysis may be completed within a shorter time period also. So analysis is being performed, and now our analysis is complete. So after the completion of our analysis, the first thing to check is whether the number of modes that we ask the software to generate while defining modal cases is sufficient or not. And we saw, or we discussed in our previous lecture, that if the number of modes that we have stated in our model includes 90% of the total seismic weight, then those number of modes is sufficient. Otherwise, we will have to increase the number of modes. For that, you can either go to Display and Show Table, or you can go to the Model Explorer on the left hand side of our interface, go to Tables, Analysis Result, and Structure Output, Model Information, and Model Participating Mass Ratios. Right click and click on Show Table. We see that we defined 12 mode cases for our structure here, and for this 12th mode case, the cumulative sum of the modal mass is 1 and 1 in both x and y direction. That means 100% of modal mass have been included in this 12th mode case, up to this 12th mode case, and also the value of Rz, Rx and Ry is also 1. So then 12 number of degrees of freedom or 12 number of modes of vibration, not degrees of freedom, 12 number of modes of vibration is sufficient for dynamic analysis or for response spectrum analysis. You check this period of vibration and these modal masses or modal participating mass ratios yourself also. We also discussed about it in our previous lecture. I will just close this. And now I want to go to base shear. I want to check base shear for our structure here. So let me just increase on this, or let me just click on this plus sign for base reaction and right click on base reaction and click on show tables. So our base reaction is being displayed for all of our load cases. We do not want for all load cases here. So we have to filter this output case. Just right click here and then click for EQX, EQY and response spectrum, that is RESP, SPEC. We only want base reaction shown for these three load cases and then click on apply multiple item filter. Now what you see here is that the base reaction for our EQX direction is 206.5102. Just note down this value. I will note down this value 206.5102, and the base shear for our EQY is 225.5916. This is for EQY. And then our response spectrum base shear value is 17.79 for X direction and then 18.5355 for Y direction. This is coming out to be a very low value as compared to our base shear for static load cases, that is EQX and EQY. Now we have to perform the base shear scaling. So let me just go to IS 1893 code and show you what it says is that in clause 7.7.3, dynamic analysis may be performed by either the time history method or the response spectrum method. When either of the method is used, and this is important, the design base shear estimated shall not be less than the design base shear calculated using a fundamental period TA, where TA is as per 7.6.2. That means our base shear that is calculated from the response spectrum method should be at least equal to the base shear calculated from the equivalent lateral force procedure. But we see in our model that our base shear for response spectrum method is very low as compared to those from ELF or equivalent static method. So now we have to perform base shear scaling. And the objective of performing this base shear scaling is that we want to have our structure the minimum strength that is governed by the static method. So we saw that our equivalent static method gives us a particular design reactions or design forces, and when we design our structure we get a minimum strength of our structure. So the minimum strength that we get from design using response spectrum analysis should be at least equal to the minimum strength obtained from the equivalent static method, and for that we have to perform the base shear scaling. So how do we perform base shear scaling? We do by changing our scale factor here. What we did previously was that we used the scale factor of I into G by 2R. Now our scale factor will be changed to a value of I into G by 2R into the value of base shear for static method in X direction divided by the value of base shear for response spectrum load case in x direction, and similar formula for y direction also, Ig by 2r into Vsy by Vrsy. Now we have our value of base shear in x direction due to from static method we got to be 206.5102 divided by, we got the response spectrum base shear in x direction is 17.79. So what we have to do is, we got this value of this factor to be 11.61. So you have to multiply this 981 by 11.61. And similarly for y direction, you have to multiply this 981 by, for y direction we got this static base shear in y direction is 225.5916 divided by, I'm using these values from the value that I noted previously. You should have also noted it. If you haven't noted, you can go back to my video and look at those values also. And then VRSY we got 18.5355. So when we perform division, we get this factor to be 12.17. So this will be our new scale factor now. So let's go to our model. You don't have to perform the multiplication here itself. Our ETABS model will also perform these multiplications. Now what we have to do is, we have to unlock the model here. Go to define and go to load cases, response spectrum load case. You have to modify it. Now for acceleration in x direction, our previous scale factor was 981. Now we have to multiply this 981 by 11.61. So 981 into 11.61, you get 1139.41. And similarly for y direction, 981 into 12.17 into 12.17, you get 11938.77. So these will be our new scale factor, and then click on OK. OK. Now rerun the model. So it will take time again for this model to run. I hope you are understanding, or you understand whatever we are discussing, whatever we have discussed till now in this fourth lecture of this response spectrum analysis. And I want to request you all to please like and comment on our videos if you are finding those videos beneficial, and also do not forget to subscribe to our channel on YouTube. Now our analysis has been complete here. Let's go to display, show tables, and let me just remove this here. Go to joint output, reactions, and no, not reaction. Go to structure output and go to base reactions and select this base reactions, and then click on OK. Now again filter this output case. Just select EQX, EQY, and response spectrum load case. Apply multiple filter item. And now if you see, our base shear for EQX and EQY case and for response spectrum are almost equal. 206.5102, 206.66, and 225.5916, 225.46. This is a little bit smaller, but it won't matter much for now. But now our base shear has been scaled, and now base shear from static and dynamic load cases are almost equal. So done, and we have completed the response spectrum analysis after we have done this. Now after this analysis, other design steps or other processes in ETABS are the same days that we have discussed in our first video lecture series on our channel, that is the design of seismic resistant RCC residential building. Now after analysis, whatever we did in those videos, we have to do that again here. We have to perform some post-analysis checks. We have to perform in those post-analysis checks, different checks have to be performed, like for torsional irregularity, for story drift, and for various other checks that we have to perform. And after, if the checks are okay, and if the checks are, or if those checks provide us values which lie within the values that are prescribed in our codes, then we can go to concrete frame design based on IS 456 code. So the rest of the steps after this analysis method are the same. So this will be the end of our fourth and last video lecture on this response spectrum analysis. I posted videos and I made videos and posted videos on this response spectrum analysis, as many of our viewers have requested to do so, and I hope you find all of our 4 videos beneficial. And if you do not understand anything, or if you have any doubt to clarify, then please comment under our videos. Our response spectrum analysis video lecture series ends here. We have one series left to be covered now, that is the series related with detailing of structures, detailing of RCC members. We will continue with that series in the future also. And I'm thinking about, since we have completed 2 lecture series now, if I come up with any interesting topic, or if I feel anything is necessary, then I will start with another video lecture series soon. Otherwise, we will continue with the detailing of reinforced concrete structure or structural members for the present. At present, we will be focusing on that detailing portion only. So I want to conclude this video lecture here today, and we will meet again soon. Stay safe, stay healthy. Thank you.